This and this will make it so people online you speak into the mic and to the microphone. So like as you can see, it's making us up just a little bit right now.
Mic check, 1, 2, 3.
Yeah. So now people online.
Sorry, where were you seeing that?
On this level right here. Okay, so this will also be it. So just make sure this is on. Okay. All right. Yeah.
Check.
So let's go to. Sorry about that. Do you have any questions? Took me like several hours to figure this out. So
how can I turn on virtual persons if they have
the virtual person is on. So if you have another person or a virtual speaker, you'll want to make sure that they're unmuted and that their camera is on.
Yeah, and so they will appear here.
Yeah, so they'll just appear on these slides.
Okay.
And if you do, want to make sure that they're on as well as they're unmuted.
Mm-hmm.
And then that's everything you can do from your end. Everything else has to be done from your end.
Okay.
I'm just going to show the rest of my team and talk them through other stuff. You have about another 20 minutes or so. Okay, so let's go to, did you do B? I did C. Did C? Yeah. Yeah, we'll go to A and then we'll go back to C. Yeah. Make sure everything's all working.
chairperson for this session, 2030 Atmosphere Theoretical to Applied Science. It's more like we cover theoretical to applied science, but I think at the end it was more theoretical. So yeah. So one of the things, we're missing one presentation. I started to learn Chinese on Duolingo, so I'm going to try my pronunciation. So Xiaofeng Xu, is he here? No? Okay, so that's the second presentation. So it's possible he won't show up. Is someone would be interested to make a presentation? Because it will create a hole, a gap. So think about this. But for now, we'll wait. So Keyvan Ranjbar is here. Okay, that's good. Not yet, not yet. Almost ready, actually, you're right. Victoria? Okay. And Shannon is on virtual. Okay, that's fine. Okay. 1 minute. Okay, so how we're going to proceed? It's their 15-minute presentation. The 15-minute presentation, but if you want that people have a chance to ask questions, so you should think about 2-3 minutes, depending of your interest of having question and also the time to answer. So 3 or 2 minutes to have question. If you take this time, then you will see this 1 minute. Well, the 3 minute there, if you see the 3 minute there, that means basically if you continue, you're actually going into the question and answer period. And the 1 minute, it means like you have to really close your presentation. Okay? So without ado, we're gonna start. I know Kevin is ready. He was ready 2 minutes ago. So the first speaker is Kevin, and then he's going to present an airborne and grounded basis analysis of an Eastern Canadian smoke event from intense wildfire in Northwest Canada. And you could read that. Okay. Without ado, you can start.
Okay. Good afternoon, everyone. My name is Keyvan Ranjbar, and I'm a research officer at National Research Council Canada. And today I'm going to talk about airborne and ground-based analysis of Eastern Canadian smoke event from intense wildfire in Northwestern Canada. Just a little bit background. As you know, wildfires are major sources of greenhouse gases like CO, CO2, and methane. And aerosol emissions from these wildfires degrade air quality and increase health risks. And we know these wildfires are mainly regional. However, smoke from these wildfires can reach long distances like Arctic, Europe, and Eastern US. For example, you can see the wildfire smoke plume from Quebec wildfire reaches Eastern Europe in the plot there. And also, wildfire affects Earth's radiation balance via aerosol emission and influences cloud microphysics and precipitation. So this project is funded by Climate Resilient Environmental Build of National Research Council, and the main effort for this project is to improve the air quality inside the building and improve the filtration. And as a part of this project, we try to characterize wildfire emission properties like optical and microphysical properties, and quantify dilution at different distance from the source. So here at the center, you can see NRC's twin otter aircraft, and to the top, you can see two different inlets that we use to sample gas and aerosol, gas inlet, rear-facing inlet, and isokinetic inlet. And also below, you can see different instruments that we had during this project on board twin otter aircraft. And also you can see the core measurement during this project. So as you can see, we can sample CO2, methane, and water vapor. And also we can measure aerosol particle size distribution, total concentration and composition. And also we can measure aircraft state and atmospheric state, including wind speed, wind direction, static temperature and pressure, and the aircraft location and airspeed and spatial orientation. So one thing that I wanted to mention here, so these aircraft that we have at NRC are research aircraft, and depend on the goal of the project, we can change the configuration, and we can have different setups to measure, to reach different goal of different projects. So far for this project, we flew over Sherbrooke in Quebec because there are a bunch of ground-based instruments at Sherbrooke University. Here you can see the location of Aeronet sun photometer and MPLCAN Lidar and Purple Air PM2.5 concentration surface measurement at Sherbrooke University. I will talk about these later in my presentation. And here, this animation shows NOAA GOES satellite true color imageries. The time resolution for this animation is 10 minutes, and this is during the day that we did those flights. And the yellow point shows the location of Sherbrooke. Here you can see how smoke from Northwestern Canada reaches the eastern part of Canada and US as well during this day. So far we did 3 flights for this project last year. So here different colors shows the flight track during this project. So we flew from Ottawa to Sherbrooke and we collected data there, and then we returned back to Ottawa, and a few days later we did one single flight to Lake Simcoe in North Toronto to collect more data. And these points here shows the location of Purple Air stations. So one thing here, we try to compare our airborne measurement with the surface measurement of PM2.5, and we limited our measurement to the altitude about 300 meters above the surface from our airborne measurement to make this comparison. And here is the result. As you can see, there is a good correlation between our airborne measurement and surface measurement of PM2.5 concentration, but our measurement shows a slightly higher value compared to the surface measurement. And this is due to the fact that during these 3 flights, the smoke plume height was above 3 kilometers, and closer to the plume, we had a higher concentration of PM2.5 compared to the surface. So here to the top, you can see the flight track for flight 1 during this project. So y-axis shows altitude, and here you can see the time series for this flight. And the color bar shows PM2.5 concentration. As you can see here, whenever we were above 3 kilometers, we were within the smoke plume, and we had a higher concentration of PM2.5. And below, you can see the optical particle counter PSD, or particle size distribution during this flight. So the y-axis in a second plot shows diameter for different beams of the instrument, and you can see that size distribution during this flight. So here you can see some of the ground-based measurement at Sherbrooke University. The first plot at the top shows Lidar signal blinking with depolarization ratio, and here you can see high signal and low depolarization ratio confirm the existence of fine mode particle, in this case smoke. And you can see different layers of smoke at altitude between 3 to 6 kilometers. And below you can see total fine and coarse mode aerosol optical depth from Aeronet sun photometer during these days, and the average fine mode optical depth during these days was 0.88, which is a big value for fine mode aerosol optical depth. So far during these days, as I mentioned, we flew over Sherbrooke and we collected 4 vertical profile, 4 spiral profile to compare with Aeronet and also Lidar. So here you can see the example of comparison between Lidar in black and PM2.5 in red. As you can see, we could detect different layers of smoke during this spiral, but there are some discrepancies closer to the surface, and this is mainly due to the nature of measurement in our optical particle counter, because our optical particle counter, the lower size range is 0.3 micron, and I think maybe because closer to the surface there are many smaller particles, that's why we have those discrepancies, but maybe Victoria in her presentation have a better answer for this discrepancy. So another thing that we tried to compare was particle size distribution from our airborne measurement with Aeronet. So here, if you look at those 2 particle size distribution, you can see that the optical particle counter size distribution unit is micrometer cube per centimeter cube. However, for Aeronet, because it's the average over total column, it's micrometer cube per micrometer square. So to make these 2 comparable, we individually weighted each sample measurement by scattering coefficient and average for the profile. Here you can see the result. So first thing that I want to mention here, our size distribution has a lower concentration, and this is due to the fact that during this day the plume height was between 3 and 6 kilometers. However, the ceiling for twin otter aircraft is 4 kilometers, so we just sample a portion of the plume. But if you look at the peak, there is a very good agreement between our measurement and Aeronet with effective radius of 0.2 micron. And then on the way back to Sherbrooke, we saw this prescribed fire, and I asked the pilot to go down and sample this prescribed fire. Here in this video, you can see how we sampled this prescribed fire during this day, and in next a few slides, I will show you some results from this prescribed fire sampling. Okay, so I start with particle size distribution. Here, gray shows wildfire particle size distribution far away from the source, and green shows prescribed fire close to the source. And as you can see here, the concentration of wildfire is way bigger than prescribed fire. However, if you look at the peaks for wildfire far from the source compared to prescribed fire, you can see that smoke closer to the source has a larger effective radius, about 1.37 micron, compared to wildfire farther from the source with effective radius of 0.2 micron. Another thing that we measure during these flights, we measure black carbon concentration. So the instrument that we used is LII 300. So this instrument designed to measure high concentration of black carbon, for example, from engine exhaust, but in this case, we use it to measure black carbon concentration of wildfire plume. So that's why it's too noisy, but still you can see a very good correlation between PM2.5 and black carbon. And here is the time segment that we measured the prescribed wildfire, and still you can see good correlation between black carbon concentration and PM2.5. And finally, I wanted to show you some example of greenhouse gas measurement for prescribed fire sampling. So the first plot, you can see PM2.5 concentration in red, and those black curve in all of those plots shows the flight altitude during these prescribed fire sampling. The second panel shows water vapor concentration, and there is an anti-correlation between water vapor concentration and flight altitude, and this is because it means that closer to the surface we have a higher concentration of water vapor. But if you look at the methane and CO2, I don't know if I can remove. Yeah, if you look at the methane and CO2, you can see there is a very good correlation between methane and CO2 concentration with the plume. And finally, I just wanted to mention we plan to collect more data during this wildfire season. And as I mentioned at the beginning, the main objective of this project is to characterize wildfire emission and quantify dilution at different distance from the source. And the result from here will be used to improve the air quality inside the building. And our result shows that the smoke plume could change far from the source. And finally, I would like to acknowledge that this project is funded by Climate Resilient Built Environment of National Research Council Canada and sponsored by Environmental Focus Area of Aerospace Research Center. And if you like to hear about the funding opportunities at National Research Center, please attend the multidisciplinary presentation tomorrow. One of my colleagues will present about environmental focus area. And also at NRC, we have different research aircraft. If you like to know more about the recent project on board NRC Convair aircraft, please attend PONEX session Wednesday morning. Thank you. Is there a time for a question?
Is there any question? So, do you have any expectations about this summer wildfire season according to climate? I don't know, according to El Niño, something like this.
About this season itself?
This summer, yeah, do you expect a lot of wildfires?
So climate data shows that we get more and more of these wildfires, but still it's too hard to predict exactly when and where we will get these wildfires. But
like the total amount.
yeah, so for example, 2023 was the highest record in terms of burned area, but as I mentioned, it's very complex issues and it depends on a lot of different things, so it's really hard to predict. Yeah.
Oui.
I noticed in your plot of the greenhouse gases from your close approach to the prescribed burn that there seemed to be a time delay in the observed water enhancement from the fire. Is this due to condensation on the tubing and just a sort of physical effect of the measurement system?
So delay, you mean compared to the smoke plume?
Yeah, compared to the PM2.5 and methane.
And the rest, yeah. So that's a well-known thing. So for the vertical profile of water vapor, in normal situation, we are supposed to get higher water content closer to the surface, higher water concentration closer to the surface. And I think this is a case because we did this flight in August. So that's what we expected to get.
Other question? Okay, I will practice again my Duolingo pronunciation in Chinese. Is Xiaofeng Xu here? No? Okay, so that means we yeah, please applaud the So we cannot start before 4. And what I was trying to say, but I said it very badly at the beginning. This is the atmosphere theoretical to apply science, but it's leading more to observation session. So I don't know if someone here would be interested to that we would discuss about observation, like what is the challenge of Lidar measurement, or what is the challenge of the the method that we're using. The last presentation, so that the next one is Lidar again, and then the next one is the final one is ceilometer. So it's also again a presentation on observation. So if someone has an idea, are we going to fill this 15 minutes? Because we cannot start the next one because some people might be very interested about your presentation, Victoria, and then we wouldn't like that. They missed that. So, or we just stop and people look at their email and they do some work. No, nobody. Okay, so we start at 4. It's in 10 minutes. So you have time to look at your email.
Special classes.
Yeah. It's not even like all of these actually are probably taking pictures.
Why is that?
That's a Western thing. For Wildfire, we don't know what happened to the light on it, but for whatever they do, it's just like they use their burned out. So, they just do that.
Right, you're right, it's important.
Okay, you know what? No further questions around it? That makes sense.
Probably expired already. Yeah.
I don't think it's actually.
Yeah. Oh, yeah.
We just got,
Actually, it's not research infrastructure and insurance. And how much would it be going to be to get insurance companies to pay out a wildfire destroyed $500 million?
but the question is, we don't just moved it there, so like, did we get insurance that also got involved in hazard and last year's? So,
And they're never going to try.
no, exactly. I expect that to happen, not,
Yeah, not the few days after.
but I expect it to start happening, like, just we put a bunch of instruments in Mexico. It can happen anywhere. This could just burn down. And I think about that. There was it's not good. I was there. So I was scared. One of the last
Wait, so
yes.
there is one except for 100 maybe 50-ish meter ring around the shipping container.
Oh, yeah.
For all the stuff that's usually housed inside. Yeah. Your instrument would be on the top of the ship.
On the ground.
I don't worry about the brown bears.
You want to do it?
I guess.
It's not very impressive. I just want to. Other than birds, people do birds. I've never considered the possibility that a bear could go for it.
It's funny because that little clearing, this little bears, so
Oh.
it is represented by the wild.
So there's small section.
Yeah.
Yesterday, we walked. Yeah.
I think it was for previous 4 or 5 years.
Yeah.
Yeah, there was a lot of. This is not bad.
It's like, I think the only issue is
Internet, that site is struggling.
yeah, still, there's a problem.
Changes to
We can do that thing.
I mean, they had something. Like at some point, it was cheaper for them to their relationship there. Oh yeah,
If I forget, just remind me of the first question.
upload data.
Let's keep it down all again. Oh, that's so fun.
So that's too. It's gonna be around 30,000.
Yeah, it's just, it's gonna be so hot, it's not a good. That is meant plastic.
I've never heard of
If the virus.
Thank you for your patience. We're just going to start 2 minutes early, so you're going to have 2 more minutes for question and observation. So the next one is atmospheric observation using the MPLCAN micro pulse Lidar network. And this is a Victoria Pinnegar. There you go. Is it Dalhousie? Dalhousie?
No, that's Western.
Oh,
Okay, well, hello everyone. My name is Victoria Pinnegar. I'm currently a PhD student at Western University, and I'm also an FSOEP student with Environment and Climate Change Canada, working with AQRD West. So what I'm going to be talking about today is predominantly the MPLCAN micropulse LiDAR network, what that is, what we can observe, and how my work is factoring into what it can contribute to. Okay, so starting off, as previously mentioned, the wildfires in 2023 reached an all-time high with 17.3 million hectares in Canada, with smoke impacting across all of North America as well as traveling across seas, producing several opportunities to research the long-term impacts of aerosol remaining in the atmosphere, as well as the evolution of aerosol as it remains. So how does LiDAR fit into studies of long-term aerosol tracking, et cetera, especially since LiDAR can be considered a point source when it comes to the data collection? So LiDAR is very resolved. So when you pull in a measurement, you get a very well-distributed vertical measurement, and you can then use that, if it's in conjunction with the network, to look at the evolution of either the turbulence within it, the dynamics of the aerosol itself, and then as well as retrieve certain capabilities or certain effects of the aerosol, like radiative transfer and possible cloud and aerosol interactions. So MPLCAN, as was sort of mentioned, is part of something called MPLNet. This is the NASA Micropulse LiDAR Network. In Canada, all part of MPLCAN, there's currently 7 sites. One of them is in London, Ontario, located at Western University. And then there's also Sherbrooke, Quebec, which we had a lovely presentation on before. There's one in Halifax, outside of Halifax, Nova Scotia. There's Stony Plain in Alberta, Eureka, Nunavut, Cambridge Bay in Nunavut, and in Toronto, Ontario. So the big goals of MPLCAN are to help develop this cross-country tracking and improve our understanding of our interactions of aerosol and smoke for the use in our air quality. So over the last 5 years, which is when the first site started, we've had several smoke events, dust events, aerosol events that could contribute to air quality. And with additional instrumentation at each of these sites, which includes sun photometers, which is at most sites except for Sandy Cove, and then Purple Air, which is the co-located ground air quality retriever, we can pull out diverse measurements for study. So being a part of MPLNet means that we have access to this global NASA-led ground-based LiDAR network. So not only do we track aerosols within Canada, we can track aerosols across the world, depending on where the LiDARs are located. And these provide 24/7 measurements, which are publicly accessible for download, which include normalized relative backscatter, which is the dominant product that I'll be talking about today, and aerosol mask, which is a complementary product to what I'll be talking about mostly today. And at the QR code is the link to the page, which you can download. So what I've been working on with help in MPLNet as well as at Environment Canada is looking at how we can characterize aerosol from clouds and other measurements automatically so that we don't have to parse through 5 years worth of data, and allow us to then use it for potentials in nowcasting or satellite validation. So my algorithm, what I work on, is producing this characterization using a wavelet technique, which takes in raw LiDAR data, or it takes in slightly less raw LiDAR data. So it takes in the attenuated backscatter measurement of a ceilometer. And it goes through pre-processing, goes through feature extraction of just signal feature extraction to pull out widths, and using widths and gradients. And then I have two methodologies for whether or not it will go through a random forest for machine learning. So it's a more dynamic threshold or static thresholding, which then comes out with a label output on all of these profiles with whether or not it's within a cloud, aerosol, or whether or not the profile is precipitation or rather than precipitation, low signal to noise. So this is not only applicable to the MPLs, I've mentioned slightly that it's also applicable to salometers, which are a much more widespread instrument, both of which are LIDARs. Salometers are located at every airport. Very important for the possibility of air quality forecasting, which will be talked about after this. So to start off, this is what we would like to call a dust event. So this was March 5th, 2022. The very top profile, very top is over time and on the X and altitude on the Y. And this is an NRB measurement. So from the 10 kilometers coming down, we have a cirrus cloud. And below that cirrus cloud is a stratified, very strongly scattering aerosol layer. So one of the biggest things that this algorithm does that's a little bit different than some of the other aerosol masks, including the MPLNet mask that comes out that is available, is that the emphasis on this algorithm is to find these stratified layers that could have an effect on air quality, potentially downwind. So pulling out this, or using the algorithm, the very bottom plot is the profiles being split up into either cloud or aerosol based off of, in this case, the peaks and the static threshold of aerosol scattering. So we can see this stratified layer, which if we put it into a dispersion model, we can find whether or not this is going to affect a community. Most likely, it will affect a community based off of the downward direction, which it's, or the downward direction, which it seems to be falling. So dust is a little bit more interesting in the sense that every February we start up with our dust season, and because of our 5 years of measurements, we were slowly but surely developing a data set that will be able to more easily characterize the intricacies and dynamics of this dust season. So one of the bigger things and one of the most important things for potential air quality forecasting and resilience is smoke. And so across our network, it's a very easy possibility of having concurrent or consecutive air quality events. So in this case, we have a smoke event that occurred October 17th of 2024, a very, very late fire in the season that occurred in the northwest of the US. And not only was it detected in London, Ontario, it was detected in Sherbrooke, it was detected in Sandy Cove, it was detected in Toronto. It had the same relative vertical structure across all of these sites. So we were able to pretty much confirm based off of trajectory as well as the physical measurement that this was most likely the exact same plume that was crossing all of these sites. And looking at this and applying our algorithm to it, we're able to see that not only does it catch it, it would be able to, in inputting into a further dispersion model, we would be able to figure out whether or not eventually it would touch down. In this case, obviously, since it made it to Halifax without a significant change in altitude, it most likely ended up somewhere in the ocean. But or it could have ended up in Europe. But I currently don't have a slide that says where it ended up. But yes, the trajectory of this plume, when we went through and used the back trajectory from high split, we tracked the we tracked it all the way back to a fire in Northwest US when we were looking at not only starting the trajectory in London, but also starting the trajectory in Sherbrooke and starting the trajectory in Sandy Cove. The size distribution of this plume seemed to cover nearly all the way from London all the way to Sherbrooke with a slight variation in time. But it did pass over a significant part of Canada, including nearly to across several places, which would be very good to study in Manitoba, but also cross most likely over Saskatchewan, which in the future in our development, we are planning on putting an additional instrument in Saskatoon. So we'll not only have our measurements in the east, but we'll be able to start tracking the smoke earlier in its development. So one of the big things that we can do with this algorithm, now that we're able to pull out these plume heights automatically and run it through algorithms to pull out potential size, distribution, extinction, etc., is we'll be able to integrate it into our dispersion model, which will be talked about later, and validate it using possible AeroNet and EarthCare satellite similar algorithms, which can then be used for the study of these aerosol vertical distribution and transport. Thank you.
Is there any question?
Hi, quick question. Do you have a way to evaluate the accuracy of this aerosol cloud classification? And also within the aerosol, can you classify to subclasses?
So the easiest way with the MPLs to classify, and I very sadly don't have, I don't have the slide up here right now, but with the MPLs, we have depolarization. So with the addition of depolarization, we're able to functionally classify particles into cloud versus aerosol. There's obviously still going to be overlap in complicated situations, cause of mixing, but for the most part, when it comes to cirrus clouds, water clouds, and then smoke, we were able to functionally validate that the layers are correct. When it comes to applying it to other salometers that don't have that, we do have, currently we're running it with a co-located MPL that does have the depolarization so that we're able to functionally classify things.
Just one moment, I'll pass the mic. When you get a mic, think about an ice cream cone. You put it that way, because if you put it that way, you see, cannot hear. They're unidirectional things, so you really have to be close, okay? I'm singing, so I need to know that.
Thanks for the presentation, Victoria. Early on in your talk, you showed a flow chart of an algorithm that I think is the work that you're developing, if I'm correct. The output of which is a labeled data set that gives the type of obstruction that the Lidar is observing. Where does the original training data set for those labels come from?
So for the random forest classification specifically, the training data set is one that I am developing. So I manually classify profiles, and that is what it is currently trained on. But there are several calibrated data sets from, for example, Calypso that are at the same wavelength as the 532 MPL, which can be used in the input, but currently it's a self-labeled data set. I'm doing my best.
When to expect to have that Saskatoon site up and running?
So we are installing it this week because we're here, technically. But the window needs to go in, so I'm expecting sometime by mid-June is operation, supposedly. Yeah. Yeah. Yeah, it's been in work for a while now, so.
Thank you very much, Victoria. It was very nice talk. So there was a comparison of cartel and yeah.
Yeah.
So why it's so different? These
Yes. So this was a conversation that we had sort of started earlier, but it's kind of an important conversation to have. The MPLs are dictated by, at least like in this product, as a normalized relative backscatter product. So it's normalized to the energy of each of the MPLs. And the energy of the MPLs works a little... It's stable for the most part, but it is very dependent on temperature. So depending on whether or not a box starts fluctuating in temperature, it can cause significant differences in the normalization process. For the most part, this can be mitigated by normalizing to the most empty part of the sky. So putting the 0 point up near 15 kilometers and then normalizing it yourself is the best way to fix this.
Okay, thank you very much. And I think we sampled same plume for AirScare calibration validation campaign. And I need to look at the data exactly, but I believe we sampled these with our aircraft.
That would be incredible if you did. I will talk to you later.
Last question? Oh, oui.
Thanks, Victoria, for your presentation. It was awesome. So when you were talking about the sites, is there any specific reason that you don't consider BC? Because in recent years, it's seeing more intense fires, especially in Kelowna and that part of the area. Like, I just suggest that it's good to consider BC, like northern parts especially.
Absolutely.
And about the random forest, would you please elaborate more on it? Like, what was your decision trees and number of estimators? And what was the validation number? Like, did you use R-squared, MAE, or what was your, yeah.
So currently we'll start at the back. The random forest is running with R-squared as the validation number. The current validation for the random forest is rather low. So it's around like 0.4. It's not great, but that is mostly due to the size of my data set. My data set is only 12 days long as of right now. But slowly but surely building up better data set with the MPLs. As for considering BC, what it comes down to is purely, it comes down to both money and site availability. So, we'll come up with the money if someone would love to host an MPL. Yeah, it is absolutely on our plate that we would love to expand farther west for sure. Yeah.
Okay, thank you, Victoria. The next speaker is online, Shannon Jalali, and will present about the Environment Climate Change Canada Ceilometer pilot project, tracking wildfire smoke in Western Canada. And I can say to Shannon that probably current ceilometer will report no cloud over Saskatoon this afternoon. So, Shannon?
Can you hear me?
Shana, sorry, we cannot hear you. I see you talk. You're talking, but we can't hear you.
Yeah, I think you have to bring me into the from backstage. I'm still backstage.
So just a second. Let me turn on your. Can you open your presentation, please?
Can you guys hear me? Okay. All right. Now we're. How about now? Can you see my screen?
Okay, it's still. It seems we have small troubles. I will write to support. Because as I can see, you are talking. I can see by screen, but I don't know why don't we have any voice.
Okay. Let me also change my sharing method. Maybe it doesn't like this sharing method. Can you hear me now? Just let me know when you're able to hear me.
It's complete with my point.
Testing, testing.
Yeah, it's my mic. So you can see she's talking. Do you see this green line?
Yes, so if you click here at the sound,
I open.
no, the last one.
No, it's better. So
Can you hear me now?
great. Do you know what happens? Because as you can see, we have this green line, so she's talking.
Can you see me? Can you hear me okay? Testing, testing.
Yes, I did it.
Testing, testing. Are you able to hear me now? Just got better.
Can you show me, please?
Are you able to see the presentation? Are you able to hear me now? Just got better.
Can you show me, please? So now we can hear you. Can you tell something, please?
Can you hear me now? Can you hear me? Testing, testing. Can they still hear me online? Are you able to see the presentation? Are you able to hear me now? Just got better.
Can you show me, please?
Can you hear me now? Perhaps it's my headset. Testing. Can you hear me? Okay, I got a message that you can hear me, but for some reason now I cannot hear you. This is good. Can you hear me? Okay, you can hear me. I can't hear you. So, all right, well, I will start the presentation and then hopefully we can fix it so that I can hear you for questions afterwards. So, I see yourselves, fair enough. Okay, so thank you all for coming to my presentation. My name is Shannon Hicks-Jalali. Thanks for bearing with the technical difficulties. You've heard a little bit, you've got some spoiler alerts from Victoria, who's been working with us on the MPL and some masking, so we'll get into that later on in the presentation. I promise we will have some applied aspects to observations. So today I'm going to be talking to you about our Ceilometer pilot project. And I just realized that I might be looking at the wrong thing. There you go. Our Ceilometer pilot project, where we are using ceilometer measurements to support operational forecasting at Environment and Climate Change Canada. So we all know that wildfire smoke has been increasing significantly over the last 2 decades in Canada. And because of that, we really need more accurate tracking of where these smoke plumes are going and greater lead time on predicting those impacts to the Canadian population. So to that end, we started our Ceilometer project in Edmonton, Alberta in 2022. Just over here with a Vaisala CL51 and a Vaisala CL61. We also have co-located purple air sensors for surface measurements. And we've also got an MPL co-located with us at Stony Plain, Alberta. And we're working on bringing on the greater network of MPLCAN slowly over the next few months. And the goal has been of this project has been to determine how we can use Ceilometer and Lidar measurements to support forecasters of smoke and air quality warnings in general. So and we also are providing feedback to our modelers on the accuracy of their AQ models and providing a proof of concept in general to NAV Canada, which operates a network of ceilometers across our entire country. But we don't keep that raw data that we would be able to detect smoke. So we're working on discussions with them to bring that online eventually. So what is a ceilometer? A ceilometer is basically an automatic laser radar or LiDAR that is designed to run pretty much 24/7 in the field with minimal intervention. As I said, they are included in most AWAS stations across the country, but we don't get those profile measurements that you would have seen, that you saw from the MPL. So what it does is it measures a vertical profile in the atmosphere where it sends a pulse laser beam, be it 532 nanometers, or in the case of our Vaisala instruments, it says a 910 nanometers, so it's an infrared laser that scatters off of cloud or aerosols. And then the amount of light that's returned is proportional to the density and scattering properties of the material that it's interacting with. And so these are extremely useful for forecasting because we can provide near real-time measurements of smoke, aerosols, clouds, fog, freezing layers, just to name a few features that we often see and I'll highlight in this presentation. We can get profiles, vertical profiles up to, depending on the model, 12 to 20 kilometers. At very high vertical resolution of 5 to 75 meters. And depending on our model, we can look at just the backscatter, but we can also look at the polarization or how much the polarization of the light changes once it interacts with the material above. So just an example of what these look like. You've seen a few examples from from the MPLs and MPLCAN and MPLNet. But I'm mostly going to focus on the Vaisala instruments that we've had installed. So these are backscatter profiles from a CL61, where we have 1 minute vertical scans from 0 to 15 kilometers altitude over 24 hours. And we can get a lot of different information out of these profiles, where we can see a smoke layer on this date on August 15th. That's descending over the course of the day. We have liquid clouds above, forming above the smoke layer. We have precipitation later on in the day. and some cirrus clouds above. This backscatter profile or image is what you would typically get from any CL51, CL61, and also the NRB signal from your MPLs. The more newer instruments like the CL61 or an MPL will also provide the information on the depolarization ratio, which is basically a function of how much the polarization of the light changes from its original configuration upon return. So more spherical particles, like smoke or liquid, like rain, will have lower depolarization ratios. In this case, I'm showing those in red, and the higher depolarization ratios that where material is less spherical, like ice or smoke or dust, or in some cases new smoke or ash, would be up in this higher range, would be in the blue range. So in this case, we can sort of do a typing of the aerosols that we're looking at. For example, in this layer, we can say that, okay, it's most likely smoke because we're showing up in lower depolarization ratios. In the bottom boundary layer, we're looking at probably some smog or some smoke mixed with dust because it's slightly less fair. We can look at the water phase where we have liquid clouds versus ice clouds. And all of these have different applications across forecasting. So I've shown where we can see smoke, and we can see different types or dust or smog in the boundary layer. That's for air quality. But we can also look at different features as well. One of the more interesting features is the freezing or the melting line that often shows up within precipitation of our in our measurements from our CL61s and our CL51s. So the melting line or the freezing line is just essentially the altitude at which the temperature profile drops below 0 degrees Celsius. So in this case, this is our forecast model where we're seeing that it's predicting the point where it goes below 0 to be around 1,800 meters. And we can see in our CL61 backscatter image, over 24 hours, this is on April 9th, actually, of this past April in Edmonton. We across the entire day, and then there's this line that goes through the precipitation over the course of the entire day and gradually descends. And that is the freezing or melting zone. And we can see that corroborated with the depolarization ratios, where we have high depolarization above that line, indicating that we have some snow or freezing precipitation, and below the line we have liquid or mixed precipitation. And why is this important? This is important for particularly important for aviation forecasting, because they really want to know if there's a potential for icing of any planes going across this altitude region. It's also important for our public forecasters because they want to know if there's going to be mixed precipitation or a chance for freezing rain and icing on the ground. In addition to the freezing line, we can also see fog. Fog is the absence of signal in our ceilometers, because what happens is when the fog forms, it will completely attenuate the entire signal. So we'll see here we have precipitation and clouds earlier in the day. We have some fog forming around 12 UTC, which is early morning in Edmonton on November 10th. And then as the fog begins to lift, we're able to observe the cirrus clouds above or high altitude clouds at 6 kilometers. And this fog was corroborated by observations at the Edmonton airport. They predicted freezing fog with the, they observed freezing fog at 1300 UTC until 1800 UTC. And this is only about 20 kilometers away from the ceilometer, so they agreed quite well. And this is also useful for airports as well as public aviation. So this data is being made available for multiple sites internally only at this point to our forecasters this summer as part of a pilot project. It's very much in beta testing mode. But we're providing near real-time observations from a few ceilometers that we have operating at Stony Plain, Squamish, and East Trout Lake in Saskatoon. This is a new site. Hopefully this will be up and running in the next couple weeks, where we provide these backscatter measurements where they can look at all of these features over the last 72 hours, depolarizations, as well as comparisons of PM 2.5 concentrations with our air quality models, so that they can confirm whether or not a plume that's predicted in the model is actually observed in real time. We also have some products under development for our forecasters that are going to be released in the coming months. And we're also working on bringing on online some of the MPL sites to fill in the gaps along the eastern Canada. So the Victoria has already presented her automatic detection algorithm, which is great. So you've seen her masks. We're using that same detection algorithm with our Bisalis CL51s. The idea being that if we were able to bring the Nav Canada network online, we would be able to use that same masking and smoke detection algorithm across that entire network. And so we're able to get altitudes and the width of the plumes, and then we feed that into our dispersion algorithms, forward dispersion algorithms. So the idea being that we can then predict where the smoke will go and if, when, and where it will reach the surface. So this is an example of one of those events. This is from this past summer on August 14th. We observed and detected a smoke plume at the Stony Plain Salometer in Alberta at 20 UTC. And then we initiated a 48-hour projection of where that smoke would go. This projection shows all the particles that are within 50 meters of the surface. So really we're focusing on surface impacts. And we saw within our dispersion models, it predicted that the smoke would arrive in Calgary around 17 UTC the next day. And sure enough, we were able to observe that with the FEM in Calgary, where we observed a spike in PM 2.5 up above 100 micrograms per meter cubed, which gradually fell over the course of the day. The interesting thing here is that on this date, the model underpredicted the concentrations of the PM 2.5. And it was the forecast or the air quality health index needed to be amended as the smoke arrived. So we're hoping that by doing these forwards, we're going to be able to provide greater lead time and better warning for our forecasters, so that they can make a decision on whether or not they need to issue a air quality statement or a warning, as the case may be, depending on the concentrations. We'll be providing this as a map to our forecasters. We're looking at two types of layers. We're looking at a total impact layer that you see here, where we'll be highlighting certain forecast zones for the forecasters. Oops, sorry. And then also providing a time series layer, where they'll be able to flip through and see when different regions will be affected. So in summary, we've seen that the LiDARs and salometers are very reliable for tracking the smoke, as well as providing near real-time observations. And we're working on this internal website tool for our forecasters for this summer, which we'll be testing. And then we're also just continuing conversations with our various collaborators on improving our products for our forecasters. And with that, I'm happy to take any questions. Thank you. Oh, I see that the slides aren't changing. Hopefully you guys were able to see the rest of that. I'm not able to hear you all still. Thank you. Working now. Okay, good. Oh, I see that the slides aren't changing. Hopefully you guys were able to see the rest of that.
Okay, Shannon, it's Serge, the convener. There is a delay of about 15, 20 seconds. Did you hear that?
I'm not able to hear you all still.
Can you hear me?
Working now. Okay, good. Yes, I can hear you. Oh, I see the slides aren't changing. Hopefully you guys were able to see the rest of that.
Okay, Sean. Okay, it's Serge, the convener. There is a delay of about 15, 20 seconds. Did you hear
I'm
that?
not able to hear you all still.
Can you hear me?
Working now. Okay, good. Yes, I can hear you. Oh, I see.
Okay, so we. Please. Did you hear
I'm
that?
not able to hear you all still.
Can you hear me?
Working now. Okay, good. Yes, I can hear you.
Okay, so is there someone who would like to ask a question with this delay things? Okay, we could put the question in the chat and then you could hear and then reply. Is that okay? You heard that? Can you hear me?
Yes, I can hear you.
Okay, so. We will have just to stop. Thank you very much for your presentation, and thank you very much for all people who made presentation, and thank you also to the audience who actually had the patience to wait 15 minutes, not 15 seconds, 15 minutes between. Pico F. Pico.